queries are expressed as variables, okay, and formulae on these variables. Okay, so this formulae that we are looking at actually specifies the properties that we want in our required relation or in our result. Okay, so I will say these formulas that we have tell us the properties that we want, okay, for our result. Now, tuple calculus is based on predicate calculus. Okay. Now, many of you would have studied predicate calculus and logic, but if you're not, you don't need to know it. Actually, I'll just give you a briefing on it. It's a formal language basically used to symbolize logical arguments. Okay, so symbolize arguments. That's important to look at because that's what we'll be making use of. So let's give you an idea. These logical arguments, when we put up an argument, okay, these are called basically propositions. Okay, so a proposition is now a property of an object. Okay, the proposition basically specifies the property of an object through a formula that we are looking at. Okay, these are also called predicates. So that's why we have first order predicate calculus. Okay, so the properties are expressed as predicates, and these predicates can evaluate to true or false. Basically, a proposition can either be true or it can be false. Okay, so to give you an idea of what we are looking at, let's say we have a statement in English saying John is a bachelor. Well, I don't know if he's a bachelor or not, but we're looking at a statement. Okay, so how do I put this in more formula kind of terms? In English, if I was doing it, I would have said is a bachelor. Okay, so I'm now looking at the fact that I could have variables. Is a bachelor John? That's how I would interpret it. Okay, so this becomes my predicate, this becomes my variable. Okay, these are actually noise words now for me, so I could just look at the fact that I'm saying bachelor John. Okay, now this has only one variable, so it becomes a monadic predicate. Okay, supposing I had something like this, t, x, and y. Now this is making more formulas that we would want to make use of. Okay, these are words in English, becomes difficult to understand. But if I say t, x, y, I could make a representation saying that x is greater than y. So if I say John is, by greater over here, I would mean taller. John is taller than Jim, maybe. Okay, so t of xy, John is taller than Jim. That's how I would interpret that predicate. Now it could either be true or false, depending on what are their heights. I don't know that, but this is what I'm trying to say is the proposition that I'm putting across could evaluate to either true or false. Okay, now this has two variables, so it's called a dyadic predicate. Okay, just information for you right now. We really don't need these terms that we will be using in SQL, but when we start solving, we will need these concepts. Okay, let's look at something else that makes it more logical. We can connect predicates using connectors. Okay, so and, or, not, and implication are the four connectors that we can use on our predicates. So let's say we interpret a statement like x is a person to be p of x. Okay, and I say x is mortal, I will write this as m of x. Right? What does p of x implies m of x mean? How do I interpret this statement in English? This would tell me all men are mortal, because it means if X is a person, then it implies that X is mortal. Okay, so that's how I would interpret the statement. How would I interpret this? Maybe. Okay, so audible and visible. So let's carry on. Okay, so how would I interpret that statement? DBMS, Oracle, and comp something. Okay, so I would interpret the statement as Oracle is a DBMS and the company that manufactures Oracle is Oracle Corporation. Okay, so that's how I would interpret it. Okay. Now, what we also need to look at the fact is a predicate can have quantifiers. Okay. So quantifiers are something that tell me how much. And if you realize, we needed quantifiers even when we looked at relational algebra, because we had words like at least one, all, and things like that. Okay. So the quantifiers that we look at over here is for all. Okay. This stands for all, and there exists. Okay. So that exists implies that there is at least one. Okay. So if I say for all X P of X. Okay, this is what I'm looking for all X P of X. What does that mean to me? Okay, it means that everything has a certain property, because I'm saying for all. So everything in the universe has that property. Okay, now I can also say, if I'm saying everything has a property, I can say that I can deny, okay, that something lacks it. Okay, deny, how do I put something now? Okay, I'll say yes. Okay, something lacks it. Okay, these are important because we need to look at, this is A and this is C. This is a, okay, so deny that something lacks that property. Okay, so for all X, P of X tells me everything has a property, and it is equivalent to me trying to find out that if I can deny if there is something that lacks that property. Okay, the next thing is the exists X that has the property P of X. Okay, what it means is there is something in the universe that has that property. Okay, in other words, the equivalent to it is I deny that everything lacks that property. Okay, so if I'm putting this in equivalent terms, I can say for all X P of X, okay, is equivalent to me saying there does not exist in X, okay, that does not have this property P of X. Okay, I cannot find an X which does not have this property. Okay, that's the equivalence of this. And the other equivalence is, if I have, there exists X P of X. The reason why I need this is because sometimes while solving, I may need to look for an equivalent expression while solving it. Okay. So here the exists as P of X is same as saying for the entire universe, I cannot find this property. Okay. So that does not exist for all X. Okay. Such that this property does not exist. Okay. So these are the equivalent forms that I look at when I have my quantifiers. Okay. Now, let's look at something more. If I say all men are mortal, the first way I interpreted it was P of X implies M of X. That means if X is a person, then he is mortal. Okay. But now what I'm going to do is, since I know quantifiers, I'll say all men are mortal can be written as for all x, okay, P of x implies M of x. Okay, because I know quantifiers now. So I'm putting it this way. Okay. Another expression. Every apple is red. Every apple I've said. Okay, so every implies all. So I say for all x, okay, if x is an apple, implies x is red. Okay, that's the next statement. Let's look at something else. Some men are clever. Okay, now some is different from every and all. I'm looking at a subset over here. So in that case, I do not use the for all. I use the there exists clause. Okay, so there exists x. Okay, x is a man and he is clever. I cannot use an implication over here. Okay, because I'm looking at a subset. So I'm saying there exists a man and he is clever. So that gives me a subset of the entire universe that I have. Okay. Let's see how I could interpret this. For all x, okay, I of x implies, say, P of x or N of x. Okay, this is or. How can I interpret this? For all x, okay, if x is an integer, then x is either positive or x is negative. I know that this is true for any integer in my set of numbers, right? So I can say for all x, if x is an integer, x is either positive or negative. Simple terms, any integer is either positive or negative. Okay, that's how I could interpret it. Okay. Let's look at one more concept. We won't solve any tuple calculus problems today. We will solve them in the next class. Okay. And if this becomes a problem with the Jamboard integration, I will think of some other way of doing this. Okay. So what we need to look at now is a concept called free and bound variables. Okay. And the scope of these variables. Now, a variable can be free or bound if it is attached or bound to a quantifier. Okay, so let's look at this. So let x be any variable, and the predicates that I form are called well-formed formulae if they follow the rules of creating those formulas. So for the rules that we looked at are the quantifiers and the connectors. Okay. There's also something called a safety of expression. It also, we can even look at this in relational algebra. Remember, when we're looking at something theoretically, we have a universe of values that can come into play. Okay. So if I say x is not equal to 1, okay, so there could be an infinite set of values where x is not equal to 1. Okay. Now, theoretically, looking for these values degrades performance. I'm looking at the word theoretically. Okay. When we look at SQL and practically, we are restricted to the set of values in our table. So the DBMS knows exactly what is not equal to something because all the rest of the values in the table become not equal to, okay, to that particular value that I'm looking for. Okay. So there is a finite set of values I'm searching for. But in theory, we have an infinite set of values. Okay. So to make our expression safe, I should not say, give me a value, say x is not equal to 1, because I could have infinite values that are not equal to 1. Okay. So looking for tuples that satisfy this theoretically is impractical. But if I say x equals 1 and do not give me this tuple, I'm restricting my set that I'm going to be given. Okay, so that's just with safety of expressions that I'm looking at. The same holds true in tuple calculus. But right now we are not looking at safety of expressions. I mean, we're not looking at theoretical expressions because we want to make use of it into practicals. Okay, we want to convert this later on into how we can look at it for SQL. Okay, so that is a different matter. So let's look at scope of variables. Okay, so free and bound variables and their scope. Okay, so every occurrence of a variable x in a well-formed formula is bound by the quantifier which it occurs with. Okay, so let me tell you what I mean by that. If I say for all x, in fact, what we were doing is we were doing free and bound variables. Most of our variables were bound in the previous case. But let's look at this. For all x, w. Okay. Or if I say there exists x in w. Okay. Where w is my well-formed formula, which is a formula built on the predicates that I know of and the connectors that I know. Okay, that are legal, I should say. Now, the moment I do this, it implies every occurrence of x over here is bound to whatever occurrence of x that I have here. And similarly for this, every occurrence of x is bound to whatever occurrence of x that I have there. Supposing I did something like this. Okay, for all x, p of x, I'm not looking at whether this proposition is true or false right now. But I say for all x, p of x implies r of x. Okay. If you notice, this x is only bound to this. It is not bound to this. Okay. In other words, here, x is a bound variable. In this particular location, x is a free variable. Okay. If I want to give you an analogy to make this understandable, it is like in a programming language, a global variable and a local variable. So when you declare a variable called x in your program, right at the beginning, the scope of x is the entire program unless it gets hidden by an x that you declare in a function. Okay. So now if you declare an x in a program right at the beginning, which is global, that value of x becomes the same throughout the program. Okay. But if you have defined x in a function, the value that x takes in that function is only localized to that particular function. Okay. So the value of x in that function may be different from the value of x that you're making use of in a global setup in your program. Okay. So I hope that kind of made sense between the x that you use here and the x that I have used over here. So this is bound. So a bound is very much like the fact that you're binding it to a particular localized set of values or to a localized function. Okay. So if I said for all x, now I'm going to do one thing, p of x, okay, and q of say y. Okay, I have this. In this particular case, x is a bound variable, whereas y is a free variable. And just like I said in a programming language, I could use the same variable name, but the meaning or the value is not the same. I could have just as well have called this x. It would not change the definition or it would not change the predicate outcome of that particular predicate that I have put in. Okay. So this is one point that we need to note. I will stop at this. We will look at queries in the next class.